second lecture on Frobenius-Fuchs method. We shall consider few examples and carry out the singularity analysis of the examples. Before going to the example proper, let me remind you that the second order linear homogeneous differential equation can be written either in these three forms. For regular point, P0 is not equal to 0 and P1, P2 are finite. If these conditions are not satisfied, then the point under consideration is a singular point. So for singular point, either P0 is equal to 0 or P1 or P2 may diverge. In terms of Q, the singular point either Q1 or Q2 diverges, and at a regular point both Q1 Q2 are finite. For removable singular point, one defines to carry out the singularity analysis, that is the type of singularity, we define x functions x1 and x2. For removable singular point, x1 x2 are finite. And if not, then either x1 or x2 are infinite, then it is a non-removable or essential singular point. With this knowledge, we first consider the Legendre differential equation. The Legendre differential equation, or the so-called associated Legendre differential equation, arises when one wants to solve Laplace's equation or such Poisson equation, etc. In spherical polar coordinates, then the theta equation gives rise to associated Legendre polynomial. If we want to solve Laplace's equation for spherically symmetric cases, that is phi, the solution is independent of phi, then this theta equation leads to Legendre differential equation. The Legendre differential equation is one minus x square y double prime minus twice x y prime plus alpha y is equal to 0, where alpha is real finite quantity. In most of the textbook, alpha is written as n into n plus 1, but for the Legendre differential equation, alpha need not be of that form. It is any real quantity, and for the finiteness of the solution demands that alpha has to be an integer. So first, what is P0? So for Legendre differential equation, P0 is 1 minus x square. P1 is minus 2x and P2 is equal to alpha. At x is equal to 0, P0 is 1, P1 is 0 and P2 is alpha. So that means it is a regular point. X is equal to 0 is a regular point of Legendre differential equation. At x is equal to plus minus 1, P0 is 0 and P1 is equal to minus plus 2 and P2 is alpha. So it is a singular point. Now the task is to see what type of singular point is it. So we define the function Q function. So Q1 is, you know that it is x minus a times, Q1 is P1 by P0. So in this case it is minus twice x, 1 minus x square, and Q2 is P2 upon P0 So at x is equal to 0, both q1, q2 are finite. At x is equal to plus minus 1, both q1, q2 diverges. So for x is equal to plus 1, this is equal to a. Note that this is a. So we define x1 point, x1 function. This is x minus 1 q1. So this all together minus x minus 1 2x 1 minus x square. So we divide it into, we split factorize it into 1 plus x and 1 minus x, and the result is this tends to 1 as x tends to 1. x2 is equal to x minus 1 whole square times q2. So it is, we write it 1 minus x whole square alpha times 1 minus x square. So 1 cancels out, so this is alpha times 1 minus x upon 1 plus x. This tends to 0 as x tends to plus 1. So both are finite. So we conclude that x is equal to plus 1 is a removable singular point. Point of the Legendre differential equation. Now come to the point at x is equal to minus 1. What happens to x is equal to minus 1? x1 is this time it is x plus 1 minus 2x 1 minus x square. On simplification, this comes out to be 1 minus 2x by 1 minus x. This tends to, when x tends to minus 1, the denominator is minus 2, and this is so when x tends to minus 1, this is plus 1. So this is plus 1. As x tends to minus 1. So again, it is a removable singular point. It is a removable singular point. So we conclude that for Legendre differential equation, x is equal to 0 is a regular point, and x is equal to plus minus 1 are removable singular point. Now we consider Harmonic differential equation. Harmonic differential equation arises one thing more. The removable singular point for Legendre differential equation is plus minus 1. These are the removable singular point, and this equation arises when one puts u is equal to cos theta in spherical polar coordinate. So the range of u is between plus minus 1, and the singular point of this differential Legendre differential equation matches with this. Now we come to the Harmonic differential equation. Harmonic differential equation arises in the quantum mechanical treatment of linear harmonic oscillator. A linear harmonic oscillator with energy E oscillates between the amplitude plus minus a square, where a square is governed by this. So as the energy increases, the amplitude increases. So for a oscillator with very high energy, the particle swings between plus minus infinity. So the Harmonic differential equation is y double prime minus twice x y prime plus alpha y is equal to 0. Again, alpha is real finite. And for the it will be still later for the solution to be finite for plus minus in the asymptotic region, alpha has to be an even integer. Now here we see that P0 is equal to 1, P1 is equal to minus 2x, and P3 is alpha. So since it is a constant and is equal to 1, there is no scope of P0 being 0. So the only scope is that this is again on alpha is finite, so P2 is finite. Only the singularity analysis needs attention on P1. So we see that P1 is equal to finite for all finite x. So any finite value of x is a regular point, and it is infinite as x tends to plus minus 1. So so to say, the Harmonic differential equation has singular point at plus minus infinity. And as we are talking about that, as the energy increases, the oscillator starts oscillating with higher and higher amplitudes, and for an oscillator with very high energy, it oscillates between plus minus infinity, which are the singular points of Harmonic differential equation. Now we go to Legendre differential equation. The Legendre or associated Legendre differential equation, the Legendre differential equation, or strictly speaking, associated Legendre differential equation arises when one wants to solve 1 minus x y prime plus alpha y is equal to 0. So when one wants to solve the hydrogen atom problem in quantum mechanical treatment of hydrogen atom problem, the radial equation leads to the associated Legendre equation, whose simplified version is the Legendre differential equation. Now here P0 is equal to x, P1 is equal to 1 minus x, and P3 is alpha. Again, we will see that when one puts the requirement that the Legendre differential equation has to be finite at x is equal to infinity, in that case one needs to change alpha by an integer n, non-positive integer n. Now here we see that at x is equal to 0, P0 is equal to 0, although P1 is equal to 1 and P3 is alpha, although P1, P2 are finite, P1, P2 are finite at x is equal to 0. Since this is P0 is 0, it is a singular point. So x is equal to 0 is a singular point. There is another singular point at x is equal to infinity, in which case P0 and P1 goes to infinity. So we define Q function. Q1 is 1 minus x by x and Q2 is equal to alpha by x. As x tends to 0, both Q1 Q2 diverges, so we consider x1 function. X1 function is x minus 0 times Q1, which is x times 1 minus x by x is equal to 1 minus x, and this tends to 1 as x tends to 0. And x2 function is x minus 0 whole square Q2. This is equal to alpha x. This is equal to alpha x and tends to 0 as x tends to 0. So we see that both x1, x2 are both x1 and x2 are finite. So x is equal to 0. X is equal to 0 is a removable singular point of Legendre differential equation. Note once again that this Legendre differential equation, as I have stated, arises from the radial part of spherical polar coordinate. The radius vector in spherical polar coordinate ranges from 0 to infinity, and these are between the two singular points of the Legendre differential equation. Another differential equation of very important in physics, and you will find several books are written on that particular differential equation itself, is the Bessel differential equation. The book of Watson on the Bessel function is a world famous text on mathematical physics. This differential equation arises from the rho equation of cylindrical coordinate system, rho phi in cylindrical system, rho phi z. When one wants to solve Laplace's equation in cylindrical coordinate system, then this leads to the Bessel differential equation. The differential equation is x square y double prime plus x y prime plus x square minus alpha square y is equal to 0. This is the Bessel differential equation when alpha is a real finite quantity. Now we see that here P0 is equal to x square, P1 is equal to x, and P2 is equal to x square minus alpha square. So at x is equal to 0, P0 is equal to 0, so it is a singular point. We define Q1 and Q2 minus x square. Both Q1 and Q2 diverges at x is equal to 0. So go to x1 function. At x is equal to 0, capital X1 is 1 and capital X2 is minus x square. So x is equal to 0 is a removable singular point. So x is equal to 0 is a removable singular point of Bessel differential equation, and there it has another singular point which lies at x is equal to infinity. At x is equal to infinity is another singular point, and rho of cylindrical coordinate system ranges from 0 to infinity. So we are not looking for the singularity that persists at x is equal to minus infinity. So our concern for Bessel differential equation is concerned between the two singular points. One is at the origin and other one at the positive asymptotes. Now come to the other differential equation. These four differential equations we have talked about are included in your syllabus, but the next one that next three that I am going to discuss are not included in your syllabus. The first one is the Chebyshev differential equation. Chebyshev differential equation. Let me V Chebyshev differential equation. You see that this is P0, so the x is equal to plus minus 1 are singular points. So Q1 is equal to minus x by 1 minus x square, and Q2 is equal to alpha 1 minus x square. And when we go to x1 and x2 function, we see that x1 and x2 are finite. Check it. Check that x1 and x2 are finite at x is equal to plus minus 1. So they are the removable singular point of Chebyshev differential equation. There is other one, the hypergeometric differential equation. The hypergeometric differential equation is x into x minus 1 y double prime plus 1 plus a plus b x minus c y prime plus a b y is equal to 0. Obviously x is equal to 0 and 1. Obviously x is equal to 0 and 1 are singular points. And you see which one are removable points or not. Check for type of singularity. That is whether it is essential or non-essential. Confluent hypergeometric differential equation. This is c minus xy prime minus alpha y is equal to 0. Obviously x is equal to 0 is a singular point, and it is a removable singular point. Till now we have considered the examples of mathematical physics, examples of interest in mathematical physics, where the points singular, we have the singularities, and the singularities are removable singularities. Now we come to we shall consider few differential equations which have essential singularities. Let us consider differential equation having essential singularities, and we will come to easy conclusion for checking the singularity, working definition of singularity. That's a dE, then we are considering dE with essential singularities. Consider this differential equation. We have considered three differential equations, 1, 2, 3. Say that for each of these differential equations, x is equal to 0 is a singular point. X is equal to 0 is a singular point. So this is Q1, this is Q2. All three equations. If we define x1 for first, so we define x1 for the first one. This is x1 is q1 times x, so this is 1. x2 is equal to 1 upon x for this. In this case, x1 is 1 upon x and x2 is equal to 1, and for the last case, x1 is 1 upon x and x2 is equal to also 1 upon x. So we see the singularity as x tends to 0, the under the functions underlined by red color diverges. So x is equal to 0 is an essential singular point of all the three differential equations. We conclude here that if q1 is at most of the form some function c1 times x minus a to the power 1, say 1 plus p, and there we have a rational function of x or polynomial function of x. Polynomial of x. Then for values of p greater than or equal to 0, if p is greater than 0, then this term in this q1 diverges faster than 1 by a and will be an essential singularity. And similarly q2 we write it is c2 times a polynomial, another polynomial of x by x minus a to the power 2 plus q. So if q is greater than 0, we will have essential singularities. So we may write Q1, Q2 in this form, and P, if for non-removable singularities we have, if P is less than or equal to 0, removable singularity, we will have removable singular points, and if Q is less than 0, we will have removable singular points. So that's all about the singularity analysis related to the Frobenius-Fuch method. In the next class, we shall discuss the form of the series solution and their justification, which is put forward by the first theorem of Frobenius and Fuch, which depends on the type of singularity under consideration.